We are SASC Biotechnologies, and our innovation is called the SEDD. I am Separ Askari, the team lead. I'm in charge of helping anyone that needs assistance, maintaining our shared goals, and keeping the group on track to success.
I am the detection advisor. I am in charge of making a device that can effectively detect seizures.
I am the marketing advisor. I handle the business and community relations side of SASC Biotechnologies.
I am the injection advisor. I'm in charge of making an effective injector apparatus.
I am the technology and testing advisor. I supervise the tech side of things and am in charge of testing.
One large motivating factor for this project includes the fact that a member on our team has been directly impacted by the results of this disease and has seen the serious threat it poses in a close friend. We are hoping that through our innovation, we will be able to make our friend's life and others with the disease lives easier and less dangerous.
Epilepsy is a neurological disorder affecting neuron activity, and it can result in seizures.
It affects 70 million people worldwide.
SE is when a seizure is prolonged, and when not fatal, it can result in permanent neurological damage.
However, the average ambulance response time in the United States is 9.4 minutes. Thus, an obvious problem arises. This problem is even more prevalent in developing countries, where the healthcare infrastructure is weak or even non-existent. So, here's our solution.
We propose a system to both rapidly detect and treat SE seizures through the use of electromyography and electrodermal sensors.
Our system will be comprised of two devices. First, an EMG and EDA detecting device that monitors seizure biomarkers in the patient. Second, an anticonvulsive medication injecting device.
The detector device will lie along the patient's arm. Using an Arduino 101 as its motherboard, it will monitor a patient's muscular and electrodermal activity through the use of EMG and EDA sensors. In the case that the device detects activity indicative of a seizure, it will send a positive signal to the injector, as well as alert emergency medical centers nearby. This basic prototype pictured here will serve as a rough indication for the design of the final detection device. As you can see, the device will be controlled through an Arduino 101, which will analyze incoming data from the EMG and EDA sensors. In addition, the final product will feature a piezo speaker, LED light, and a button to alert the user of critical medical information.
The injector device will be located on the ventrogluteal muscle and will be strapped to the patient. When a positive signal is received from the detector, the injector will use a spring mechanism to automatically inject anticonvulsive medication into the patient's body. The device will be comfortable to wear and hidden from public view under the person's clothes. The CAD model of the injector device pictured here will contain three major parts. The center will consist of the spring mechanism, which will automatically inject medication. The areas to the left and right of the mechanism will consist of a microprocessor, which will receive the signal from the detector, and a small rechargeable battery.
Currently, there are several seizure detecting devices. However, none are specifically designed for SE and none include a treatment apparatus. Other devices focus on contacting emergency services, while our device provides immediate treatment in addition to contacting emergency services. We will initially test the SEDD without human testing by creating a device that will simulate the EMG and EDA signals. Using this device, we can measure the accuracy of the detection algorithm and the sensor system. The EMG simulation device will be constructed by using a program to change the potential emitted by the digital to analog converter, which is then received by the EMG sensors. The EDA simulation device will be created in a similar fashion. Here is the current prototype of the EMG simulator. To the left is the Arduino Uno, which interfaces the program to the digital to analog converter. This analog signal is then connected to an op-amp circuit, which both level shifts and steps down the potential to detectable levels, and is then outputted to the EMG sensor.
Wearable medical technologies are on the rise, and the development of seizure detecting devices has rapidly increased in the last 10 years. However, this market is currently a difficult environment to bring a product to market as an individual small business. Therefore, we will be pursuing a licensing model. We will target larger medical tech companies with greater resources and experience.